Okay, hello, hello, good morning to everyone. Uh, Thank you very much for the second chance to the tuition grant. It's very nice learning experience. And thank you very much for all the colleagues, the curators that really paved the way to the talk that I'm going to give right now. So they already emphasized very nicely some of the things that right now I can avoid to say, although these are individual recordings. So let me see if I can share my screen with you. So my name is Enrique Iglesias. I come from Universidad Simón Bolívar in Caracas, Venezuela. And today we are presenting here my best comparison. So that's the first goal of this talk. But I have another very important goal during the way to these best comparisons is that I want to present some details of how to come up with a convenient structure for a comparison where you repeat resources across contributions. You would try to make these resources properties portable across comparisons, try to make them as easy as possible to upload, and to try to employ the minimal amount of different resources in this case. So in the comparison that I prepared in both curation periods are reside in subfields of applied physics, plasma and beam physics, optics, quantum optics, atom, molecules, and plasmas that are provided by the ORKG. So I give you a little bit tour, a small tour of what plasma uh, plasma state of matter is. It's well, commonly called a very hot gas, also commonly called the fourth state of matter, when the other three are the well-known solid, liquid, and gas. The interesting thing about plasmas is that they cover a brick several orders of magnitude in densities and temperatures, as you understand them, density of matter, temperature, cold to hot, but several orders of magnitude. And that means that then you find many physical systems that comply with the characteristics of the plasma. And I'm presenting many of here, flames, ionosphere, auroras, the sun that you look, the lightning bolts, and devices that are made in here in laboratories that are oriented to solve probably a energy future. So all those are plasma. In fact, most of the time, there is this quote that says 99.9% of the universe that we know is a plasma. So in the first curation grant, I prepared some comparison addressing a couple of areas of this frame that you see here, and the papers with which I populated the ORKG are joined by discussions of, well, let's say spectroscopy, meaning the tool that is discussed in these papers is the studies of the light that come from the systems that will tell you how the systems perform or what they are. In the second period, I'm being consistent with the same area, experimental plasma physics. I'm visiting now different physics systems. And here again, the concept is that unifies all this publication is a spectroscopy, but in this case, in the range of the X-rays, because there is where some of the signals that we see from the universe can be measured now with space observatories, and also because some of the properties of these space plasmas are reproduced in the laboratory and are used to help make an interpretation of what you see in the universe, okay, from these cosmic sources. So the type of information dealing with these are publications that which rate of production depends on the nature of the research. It could go from a little bit slow production when there are big experimental systems, or faster production, which is modeling, passing through instrumentation, observation. Uh, Many of these publications don't produce a big amount of instance of data. That's a relative term, of course, which is different that the data has a massive amount of bits and bytes. That's completely different. So many times when the data gets to the public, it's been already under scrutiny by the persons that were the first proponents of the research work. These tops are hot, let's put it that way, but they don't have, as I said, an explosive amount of publications. Uh, some of the papers are seminal publications. The publications are very tightly refereed and reported in relevant impact, and reported in journals have the relevant impact in the field. So, but that doesn't mean that our researchers are not exposed to a big way of data, because if you compare from 20 years ago, the amount of data, the amount of information that the digital age is providing is orders of magnitude of what it was in the past. Show video. So they need help too. And the ORKG Open Research Knowledge Graphs can come out with this help, because to start with, the ORKG can provide you with the stored metadata and progress of publication. So to start with, you will have that. But the ORKG also provides you with the structured audience of knowledge, it's called the comparison, that expands, that allows you, being redundant, to compare and present publications in support of many things: questions, answering, situations, uh, specific problems, the appearance and disappearance of ideas. It can keep up with the trends of production of research. It can make it highlight achievements of research work. Uh, can be dedicated at specific topics. Can narrate. Can tell you about the time evolution of the line of research. So so that means that we have this tool available. Our researchers can ask themselves, for what can we use this? And uh, uh, this could be some suggestions. These comparisons can be used to fast track the introduction of a new user to field, is provide an easy access to updated or improve your base knowledge information on a field, can help you contextualize a topic that you try to work on. It can even promote the preparation of proposal with a broader vision of the problem. So this is a typical paper. This is how it looks like. It has an abstract. But then if you could make a more exhaustive study of it, you will find graphs, tables, modeling of data, references, analysis. And so the information that we extract from the paper, we decided to do it at the level in between the summary in the data and an exhaustive search. Okay, so how we proceed to do this work, we decided first on an area of interest. We searched for these publications, and then we started to think about how to define a contribution such way that it will comply with what I said in my first slide, which is we need to define a convenient structure, and we need to search for convenient properties. Uh, we want the properties and resources will be repeated and portable across publications and comparison. We want to accommodate fair principles, and we also want to make a suitable comparison view. That's was also a very important driving principle behind this work. So when we talk about structure, we can say something like this. This is a bimodal kind of decision tree that allows you to classify, for example, different type of pastas. It's also, I can reduce and can avoid this yes no decision making, which is implied in there. So that's a type of structure that was very appealing to me to try to study these papers and present papers. So if we keep thinking in this frame of thinking, then we can have several companies, for example, that are producing these different types of pastas. But different companies will have different lines of production or different ways to develop them. And then it will be very interesting if you have this information classified this way and be able, for example, to say how a plot of the companies versus these production lines. Okay, so that gives an idea of how we can digitize this in a contribution in the ORKG, and that it will look like this. You will have several contributions. Then you have these yellow boxes here that this is called, they're called resources in this abstract frame. Then you have these blue squares here, which are the properties. And something that I wanted to emphasize is that now what was before kind of the outcome of the tree right now is actually where we have our input data. So, so just going to details of our contribution, uh, what's important here is that our input is uniquely connected to our contribution. So when you try to repeat these resources, that becomes a problem because resources are designed in the contribution to be general, and that is completely the opposite of what you want. You want to make a unique path that goes in between your input data and a given contribution. So what we need is somehow to differentiate these resources, and what we do is that we have to add to them an RID number. So getting in a little bit more detail of this description that I just said, so each input data has to be identified uniquely. It requires every source had to be unique, had to have a unique RID. So that makes the loading of the elements of the structure that you have here more cumbersome. In principle, the resources are not really reusable because you have to complement with this RID. Um, the other interesting thing is that if you spend this tree too much, then all these elements, as I have it right now, all these elements, all these resources belong to the same class. And then if you look into this class, you will find out that there are quite different elements that are sharing a space during these classes, and that's a little bit awkward. And that will happen if you abuse too much of the structure tree. Or put it in other words, many layers in the chain could lead to into arguably incoherence within the elements within the class. So this is how it looks. This is a graph of a structure that is provided also by the ORKG, where you have specifically three lines of of resources that start. One is atomic characteristics, plasma characteristics, spectroscopy characteristics. And as I showed before, you take one of this, you go to, for example, underneath this is charge state, and then here you see we switch to a part of the contribution that is dedicated to these property types, and a part of the contribution that is dedicated to the measure let's call it that way, and that is switched right here in this property measurement, and then you have the measurement here. And as I said, we need to have a unique connection between this and this. And when we go to the next contribution, that's very hard unless we uniquely identify these elements. So how we solve this in this second curation grant, or partially solve, or we are in the route of making a best structure, is that we left all this part of the resources support properties as a glossary that has nothing to do with the actual input of the information. And then we made the measurement part directly into the contribution in only one step. So it's uniquely connected to the contribution, although of course here we had to put these different IDs. But the benefit of this is very much easier to upload. It responds to the auto field very easily. It can be portable very easily. And then it reduces the load of using the RFIDs. And then we guarantee that there is a one-step direction, one-step connection with the actual contribution between all these measurements. Well, if you look at the graph of this new structure, it will look like this. This is in this case again atomic characteristics. Here is this part here. It's like a glossary of it. Underneath is a charge state, and as you see here, these are all the measurements, and that here is now the charge state measurement that correspond to this resource here. So actually, the diagram that I showed you a moment ago, it can be very well represented and provided by the ORKG platform. So this is a look of my comparison. I will try to connect to it. Let's see if we can do it. Uh, my colleagues really helped me a lot before in describing how the comparison looks like. So I'm not going to do it right now. The comparison is still loading. As I said at the beginning, the comparison view was very important for me. So I'm just going to show you briefly how it looks. So this is for a research program objective and what type of paper or publication we're talking about. Here is our uh, three trees of decision: atomic characteristics, plasma, and spectroscopy. And that's very nicely separated in the comparison. Uh, we have here the atomic characteristics and the characteristics that are attached to it. And right underneath it, 1, 2, 3, 4, 5, you find this the input data, 1, 2, 3, 4. And one of these characteristics is split in two, as you see here. And underneath it, you'll find again the input data that correspond to those two. When we go to another branch, then which is plasma, then again you see the same pattern. Here is the characteristic that correspond to plasma, and this is the input, which in this case is a resource, which changes depending on the contribution you're talking about. And here we have a spectroscopy. Again, it has 5 characteristics underneath it. One, two. The third one has actually, let's call it 3 inputs because it has a resource, it has a range, and also it has the units that correspond to the range. So finally, we have the last 2 of the 5 that I mentioned here above also reported. So this is the way I envision this type of description in kind of a classic paper. And this frame can be used, this frame or this structure, then for any of the purpose that the ORKG can be introduced to that I mentioned at the beginning of my talk. So I'll go back to my presentation, and uh, so I just want to tell you thank you. I think it was very nice to share with such a bright group of people that understood so well what the ORKG is for. And I really want to give a special thank you to Keir, Edin Farfar, that helped me write this wave of knowledge that I needed to learn to be able to understand this modeling. As the expert said, he also to Lars Fox, that was the driving force that made me realize that we need to improve when one has a task of preparing a model for our KG contribution. Thank you very much.